Well, we're going to be finishing off related rates today, but let's just get this out of the way. The rates of change, I should say. I want to spend a little bit of time on reminding you how to differentiate powers and logs. There's my favourite function in the world for differentiating, because even I can't screw that up, right? But we discovered that you can actually differentiate any power of x, 2 to the power of x, 12 to the power of x, 4 to the power of x, anything you like. And to do those guys, the answer is 2 to the power of x, and then you tag on a log 2. And if you want to find the derivative of 10 to the x, it is 10 to the x, and you tag on a natural log of 10. So it's that guy times this guy. And this last one, it's 4 to the x, and then you tag on a log 4. So in general, a to the power of x, where a can be any number at all, is called the base. Its derivative is the natural log of a times e to the x. Are we all familiar with how to differentiate then 5 to the x, 10 to the x, or anything else to the x? And you can, and you do get questions like this. How do you differentiate 3 to the power of x to the 4, for example? Well, if you think of this as a chain rule, isn't this 3 to the power of something? And if you want to differentiate 3 to the power of something, you get 3 to the power of something, and you tag on a log 3, and then you finish with, right, the derivative of that something. And then you just kind of make it look pretty. Are we happy about using the chain rule with weird bases, like 2 to the power of x cubed and 3 to the power of x to the 4, or 4 to the power of sine x or something, right? You can use the chain rule. Okay. Keep that over there for a minute. And then let's look at the next one in the set then. If you want to differentiate the natural log, the answer is 1 over x. But you can differentiate the log to any base you like log to base 10 or log to base 4. And if you want to differentiate the log to the base 10 of x, you get 1 over x, and you tag in an extra ln of 10. And if you want to get the derivative of log to base 4 of x, you get 1 over x, and you tag in a natural log of 4. Are we happy with those guys? So in general, the log to the base a of x, its derivative will be 1 over x, and you tag in the natural log of a. So if it was base 7, you do a log 7 here, right? Natural log of 7. And couldn't we do product rules and quotient rules with combinations of these and these, and chain rules and any other rule that you can ever think of, right? So we can now expand what we can differentiate from just e to the x to things like 10 to the x. And we can expand derivatives of not just the natural log of x, but log to the base 10 of x, or any function like that. So that has increased our scope of things that we can differentiate. So that is unconnected with what we're doing, but it's something that cropped up with my other class. So I figured out that I probably didn't emphasize derivatives of different bases for logs and exponents. So hopefully that helps. Right, so we're going to finish off related rates today. These are the last three questions we're going to be looking at. Question 7 essentially takes the depth at the depth of the water in a port. I believe it's someplace in Canada, and it's got one of the highest tide rise and falls of anywhere in the world, allegedly. And the formula for calculating what the depth of the water is in the port is given by this really ugly, oh, shooting space. Hold on a second, will I fight with my Windows? Come on. I am really good at not swearing. If you could see the problem I'm having right now with this window, you would be swearing, I tell you. Okay, I got it out of the way. Now I'm happy. Okay. So this guy tells us the depth to, the port. So you imagine this is the port, and here's the sea, and, tide comes in, tide comes out. That's actually something, Sabrina. Where are you, Sabrina? Sabrina, is tidal, you can get books now, although it's probably online. And won't it tell you the depth of the tide at any place in the world that's reasonably known at any day of the year?
Yep.
So they basically...
Even though it is online, you still, usually most boats will carry big the tide charts for the year.
Right, so when you get them, is it just a table that says at 8 a.m. this is going to be the depth, and at 9 o'clock this is your depth, and at 10 o'clock this is your depth? Is it kind of like that, just a big book with lots of numbers?
Mostly lots of numbers. It's a little bit complicated because you get complicated water movement around islands and things like that, so it doesn't perfectly match, the global model of moon and sun over here, tide goes over here. So
because things get in the way of that water moving.
Exactly. So yeah, there's some weird complicated tables, and you have to do some calculations even with the table.
Okay, so in a perfect world it would be this depth, but you have to do this tweak because of an island or whatever. Right. So this basically is probably a stylized version, right? So this is where that day numbers came from. So they probably don't do that, because if you gave people on ships these kind of formulas, isn't there a great chance they would screw it up? Unless they were good at trig. So what are we going to do with this? Well, we are going to find the rate of change of the water. And the idea behind this is, if you tell me the formula for something, and then you say, find the rate of change, find out how it's changing through time. So you can imagine at 8 a.m. to 9 a.m., is the water going up? And how fast is it increasing, right? How fast is the tide going up, right? Coming in, right? Or is it negative? How fast is the tide going down, right? At what speed, rate? So how do you differentiate an ugly guy like that? The first thing you should do is do not get distracted by ugly decimals, because ugly decimals is what you get in real life formula, right? You don't get 3t and 4x, right? You get nothing 0.123 and all sorts of weird stuff. So I'm thinking of that as just a number, and that is just a number. It's just like 2 and 3. So let's differentiate them. If you differentiate the number 7, don't you get 0? Now, if that 7 had been some ugly number, because maybe in some other port it would be, like 6.2345678, wouldn't the answer still be 0? So you don't let the ugliness of the number distract you from the process, right? A number gets you 0. Ugly number or 2 still gets you 0. Now, 5 cosines of stuff. Doesn't that make you think chain rule? So when I differentiate 5 cosines of something, shouldn't I get -5, the sine of something? And the something just happens to be really ugly like. But since it is a chain rule, shouldn't I then finish with the derivative of that something? What is the derivative of this with respect, pardon me, with respect to t?
0.503.
Yeah. Now, if it had been 2 lots of t minus 1, wouldn't you probably say, yeah, times 2, what's the problem, right? Because 2 and 1 are nice numbers, right? But I mean, if you need to, I guess you could distribute that. But isn't it 0.503t, and differentiating 0.503t gets you that guy? So you put this package together and you come up with this times this. So let's see what that is. -5 times 0.503. And we would be looking at -2.515. That's this and this, right? Followed by the sign of the ugly guy. So what we found is the formula for the rate of change, how fast the water is rising or falling, right? How fast the tide is coming in or going out, if you want to call it that, right? Any given time t, and t is, 1 means 1 a.m. in the morning, right? 9 would be 9 a.m. in the day, right? 14 would be 2 p.m., right? 24-hour clock. So the second question says, what would the change be at 9 a.m.? And it ends up being a really ugly calculation. That guy. And I'm just going to tell you the answer because I don't want to hit buttons and screw it up. It's that, and the units are meters per hour. So in this place in Canada, at 9 o'clock in the morning, the water is changing at the rate of -2.28. Doesn't that mean the tide is going down, right? The water level is decreasing, and it's decreasing by -2.28. And for you Americans, that's about -7.5 feet. Right, Sabrina, I'm picking you because you know boats a lot. If you were in a place and the tide was going out at the rate of 7.5 feet per minute, would you be amazed at that number?
Yeah, it's when it's going out that fast, that's just how fast it's vertically dropping. So never mind how fast it's moving along the beach.
Right, so that would not be a good place to go swimming, because it would probably suck you out to sea before you knew it if you weren't careful. Isn't it kind of fascinating that we can model things like that? I'm sure if you went to any of the major ports in the world, there would be guys who've already created their version of this formula and tweaked to things like the island that gets in the way that changes the true value for it. And if they've got a really good formula, wouldn't they be able to predict what the tide's going to look like in August the 14th, barring storms? That's good, good. Next one, question 8. Totally different tack. Bacteria, this one is about. The population triples every hour, and you start with 300 bacteria. Find a formula for the number of bacteria after T hours. I'll throw it open and then I'll tell you how to get it, because it's asking a lot right off the bat with very little information. You start with 300 bacteria and it triples every hour. Any idea for a formula involving T that would be able to model that situation?
$300 times 3 to the T.
Nailed it. That is exactly the formula. Now let's put in the pieces. If something's tripling, after 1 hour, it's 3 times. After 2 hours, isn't it 3 times 3, which is 3 squared? After 10 hours, isn't it 3 to the 10? right? 3 times 3 times 3, 10 times. After t hours, it's 3 to the t. What's the 300 doing at the front? Isn't that how many you started with? And I like that answer. And I hope WebAssign allows you to type that answer in. But that's not the answer I'm looking at. They did this, which I am not that happy about, but I understand it. 300 can be written as 3 times 100. And you can take this 3 and add it to this power of 3, and you now get that version of the formula. Are we okay with that? It's not the way I would go. Style points, I think that formula is fine. And if it takes it, great. And if I had a question in the exam, I would take that formula without any problems. And then it asks us to find the rate of change. And they don't ask us it by saying, find the rate of change and then find the rate of change at 2.7. They just hit you with the question, estimate the growth rate. Well, you're going to say, where's the rate of change? There's the rate of change. Estimate something rate means you're going to be finding a rate of change. So let's differentiate this guy. Now he's 100. Well, let's do this version. I like this version better. 300 times 3 to the power of t. If you want to differentiate 300, 3 to the power of t's, don't you get 300, right? And 3 to the power of t is the natural log of 3 times 3 to the t. Agreed? Derivative of 3 to the power of t is 3 to the power of t, and you tag on a log 3. Remember what we did at the start of today, right? Derivative of that guy is that. There's your answer to the rate of change. You want the rate of change at, you want the rate of change at 2.7 hours. Then just find out what 300 times the natural log of 3 times 3 to the power of 2.7 is. And that's what calculators are for. So 300 times the natural log of 3 times 3 to the power of 2.7. And the answer we get to the nearest whole number is that. So the rate of change run about 2.5, a little bit more than 2.5 hours into this bacteria, you're going to get something along the range of 2,400 bacteria per hour. That's how much it's increasing by. So if you've ever done any medical things, don't bacteria like, if you're not very good at cleaning things, don't bacteria build up really quickly. And that's how people in hospitals are almost paranoid, aren't they, about cleaning? Everything gets cleaned, disinfected over and over again. Because if you're not careful, these little buggers breed like rabbits, right? And you end up with lots of bacteria, which is bad for you. And just to show you that mathematics can get used in business, the last one, question 9. We're going to look at the cost in dollars to produce X items. And it's given by this formula. 0.0006 x squared plus 0.04x plus 5. So if I want to produce 200 tins of beans, put 200 in there, and that's the total cost, right? So this is the total cost of producing X items. This is the formula for it. Why is it so ugly, decimals? Because in real life, aren't real formula ugly, right? You know, horrible numbers. Now, you want to find the rate of change? I don't care that that's an ugly decimal X squared. Isn't the derivative just 2 times that ugly number X? Right, you differentiate X squared. And 2 times that ugly number Gets you that. And what does the derivative of this ugly guy get you?
0.04.
If I'd said to you, what's the derivative of 5x, you should look at me and say, what's he asking that stupid question for? It's 5. It's not even worth thinking about, right? If I'd said to you 3x squared, wouldn't you have said 6x and not even thought about it now? But the minute I say 0.0006x squared, isn't there a part of your brain that goes, whoa, what's going on here? And it's not a whoa. Isn't that just 2x squared or 4x squared? That's all it is. Now, you want to find for part B, oh, and by the way, do you know this fella, this derivative guy? He's called the marginal rate of change. Or just marginal function, because people in business don't like calculus. So they hide the words in their names. So you differentiate it. And you got this guy called the marginal function. What that guy is telling you is that at the X position, right, at 130 items in this case, this is the cost of producing the next item, right? It's the increase in cost. And I put an X there for some reason, 0.04. And I guess I should do that. 0.0012 times X, which is 130, add a 0.04. That's not right. That is not right. What's missing? Oh, it's 130. Okay. 0.012 times 130. That looks better. Add 0.04. I am not getting the answer I got the first time I did this. What on earth have I done wrong? Let me check the question. Wrote it down right? Yep. Differentiate that right? Yep. Okay. I wonder if I wrote the wrong answer the first time. Then I get 0.196, which is about just a little over 19 cents, isn't it? And that is essentially telling us the cost of the next item. So that's the cost of the 131st item. Now, if you want to find the actual cost, find out how much it costs to produce 131 and take away the cost of 130 and see how close it is to that number. And that's just plug that into here, and subtract the 2. And that would be the cost of the 131st item. Now, if you think that doesn't make sense, why would an item cost a different amount? If you produce a lot of things, isn't the unit cost quite small, relatively speaking? If you had a whole factory set up and you had 200 people working for you and you only made one thing, wouldn't that one thing cost the entire value of electricity, paying rent and paying wages? If at the same time you produce 200, can you imagine the cost would be different? Because you're sharing the cost of producing it amongst a lot of items. So the more items you produce, the unit cost very often tends to go down.
Okay, I did that calculation and it says it's 19.6 cents. So what do you know?
Whoa! Did we get a perfect match? Okay, it should be like 19.9, right? Or 18.7, right? It's going to be a little bit out. The fact that it was bang on is amazingly good. But don't expect it to be bang on, right? It's an estimate, right? But it'll be close to the real answer. Well, that is amazing. Perfect match. So I shouldn't have been worried about the number. It was the right number. Go figure. Next fella then, or next section. is a thing called related rates. Now, I want you to imagine that I've got a function called 4x cubed. And if I asked you to find the derivative with respect to x, I hope nobody here would have a big problem with 12x squared. Well, the concept of related rates adds another dimension. You imagine the x and a vary with time, which we'll call t. So can you imagine that the x isn't a fixed value? X changes with time, and a changes with time. And in these questions, related rates, you're not going to be asked typically to find dA by dx. What you're going to be asked to find typically is dA by dt. To find the rate at which A changes with t, because A is a function of time as well. So, analogy. Isn't it kind of like a chain rule, a function of a function? A is a function of x, right? It's 4x cubed. But x is a function of time. So isn't A a function of time? So dA by dt does make sense. Well, there is a formula for calculating it. This is one of the reasons why the dy by dx notation even exists. Because, you know, if it wasn't for situations like this, wouldn't we be just using f dashed of x and y dashed? We wouldn't bother with this notation, right? But can you see that the way this formula is written, if you want to get the rate of change of area with time, you find the rate of change of area with the variable x multiplied by the rate of change of x with respect to t. Now, these look like fractions. I know they're not, but can you see a little cancel becomes the same guy kind of thing? So doesn't this notation kind of help you understand why the formula is working in a kind of pseudo-scientific way? And it also allows us to do it. So what is going to happen in these questions is you're going to be given an A. You're going to be asked to find dA by dt. And you're very often going to be asked to be finding it at one specific value of x. So we're going to find out what the rate of change of A with respect to t is at x equals 5. And they are going to tell you what that guy is. And that guy there is almost always going to be just a fixed number. And it might have units, so I'm pretending in this case, 5's a bad choice because too many 5s here, make that 6, right? So you're being told that x changes at a rate of 6 meters a second. And you're being asked to find the rate at which A increases at this particular snapshot of time. Right, I've got my formula. If you differentiate A with respect to x, you get 12x squared times dx by dt, which is 6. So the formula that I've got for calculating the rate of change of A with respect to t is 72x squared. Do you see this formula just contains x's now? And at x equals 5 then, this formula, because 72 times 5 squared, and 72 times 25 is 1800, and I guess the units are whatever it is, meters per second, or maybe meters squared or something. And that's an example of what's called a related rate. You're finding the derivative, a rate, but it's related to another variable called t, right? Everything's in terms of changing with t. Let's make a real one. Suppose I've got A equals pi r squared. So this is very similar to homework question 1. And we are told in this question to find dA by dt. So dA by dt is the derivative with respect to x times dx by dt. And nobody noticed the variable was called r, so it's dA by dr, dr by dt. Now you differentiate this with respect to r, and you get this guy. And that's the answer to A. Now, question B starts filling in some of the details. In this case, you're being told that the radius is 31 meters, at least the one I've got. And you've been told that dr by dt is 5 meters, this percent. So the rate at which the area is changing, there I go again, with respect to t, is 2 pi 31 times 5. And if I just go 2 times 31 times 5, I get the answer 310, and just tick a pi at the end. Now I could find out what that is as an ugly decimal, but as an exact value, leave it alone. If you can leave it alone, it's better to do that. So in this story, because there was a story attached to it, there was a oil spill and the radius was increasing, right? So if you imagine as time goes on, the circle would get bigger, and it was getting bigger. The radius was increasing at the rate of 5 meters a second. So that's a very fast, right, growth. What's the rate at which the area, right, the total area of that oil slick would be? It's roughly at the 31 meter mark. So if you imagine took a snapshot when that distance was 31 meters, how much more area is being added, right? How much more oil spill is going to happen? And the answer is that much. It's increasing at that amount. Let's do a let's do a volume one. Okay. Suppose I tell you that fella, and I would like to find the rate of change when r is equal to 2, and I tell you that dr by dt is 10, right? And so this is very similar to question 3. So we want to find the rate at which the volume of a sphere is increasing when the radius is 2, given that the rate of change of the radius with time is 10, I'll put some units in meters per second. To get dv by dt, that I keep doing t, that is t. dv by dt is dv by dr times dr by dt. Let me write that again, it's a mess. Now, if you differentiate this guy with respect to r, you multiply by the power and you reduce the power by 1, you get 4 pi r squared. This fella is the fixed number 10. So you get 40 pi r squared. And that is essentially the formula that you can use to find the rate at which the volume is changing with time. And in this particular snapshot, I want to know it at 2. Well, the rate of change when the radius is 2 is 40 pi times 2 squared, which is 4. So it's 160 pi, and the units would be cubic meters per second. But if I've got this formula, can't I also tell you what the volume would be at when the radius is 10? Plug 10 there and square it. When the radius is 1.23456, can't you just plug in 1.23456 here? And the reason I can do that is that the rate of change is a fixed number very often, right? The radius is increasing at a fixed rate. It's just growing bigger in a linear way. Any questions about that one? Are we good? A new guy in town called related rates. One last question to do then for today. Let's do a version of question 2 then. In question 2, you're being given a square and it's increasing at the rate of 7 centimeters a second. So I'll draw a square. I don't know what the size of the square is, so I'll make it X. And you know that the side is increasing at the rate of 7 centimeters per second. So they've just told me that, and it's a square. And I'm being asked to find the rate at which the area is increasing. So that becomes find dA by dt. And I've defined it when X is 4. So I know I've got a square. I know that the sides are increasing at this rate. Dx by dt is 7. I'm being asked to find the rate at which the area is increasing when X is 4. So I'll start off with, I need a formula. And would you agree that the area formula for that square is X squared? Right, X times X. And now I can find this fella by doing dA by dx times dx by dt. And if you differentiate this guy with respect to x, you get 2x. And this guy is a fixed number, 7. So the formula that we have to find the rate at which area is increasing with time is this guy. And we want to use it at that one specific snapshot. So dA by dt is 14 times 4. So it's 56. And since this is an area question, it's probably going to be 56 square centimeters per second. Agree? Now, when X is equal to 2 centimeters, the rate at which the area of the square is increasing is 28 units. I won't write the units out of the distraction. When X is 4 centimeters, the rate at which the increase has changed. And when X is 10 centimeters, the rate at which the area increases will change yet again, and it will be 140. Why, as the square gets bigger, is the increase in area, right? Different, as you can see from these numbers. Why shouldn't it be just the same number all the time? The X is increasing at the same number all the time. Why is the area not increasing at the same number?
Because it's a function.
Can't hear that? Say it again, please.
Is it a function?
Well, our
Kind of a
function is causing that, but I'm geometrically, why is this happening?
Oh, it's speeding up.
Well, not technically speaking, that the sides are only increasing at that speed. And this is increasing, this is speeding up, the areas are speeding up. But what's the geometric reason for it?
The area is dictated by the sides squared. So if you have the sides increasing at
Yeah, I
fixed
getting
rate.
what you're saying, yeah.
Yeah, a fixed
a
rate,
small
then the
square
area
bit.
will increase exponentially.
A small square getting bigger doesn't increase by that much area. A big square increasing doesn't increase by a lot more. Can you see that there's a lot more area being added when it's a big square increasing than when it's a little square increasing? And so it does, as Gordon was saying, it increases exponentially. In fact, technically, if you think about it, isn't it increasing at the square of the rate, roughly?